Let me start by reviewing what we learned in the last lecture. Okay. In the last lecture, we studied how much wave would be reflected how much wave is transmitted when we have instant to wave, okay, and we expressed this instant to wave in complex notation. That means we assume that the instant wave has complex magnitude and minus j omega t minus kx, and I put k0 because we assume that this medium has characteristic impedance z0, that is rho 0 c, c0. Okay, we also assume that this medium has different characteristic impedance. We denoted that as Z1. Okay. We have different medium like this. And we denoted this PT that has also complex magnitude. And the PR similarly plus K, because this is left going wave. And the result, what we had was the ratio between the magnitude of instant wave and magnitude of reflected wave can be written by like this. That means how much reflected due to the instant wave is totally governed by the characteristic impedance of two medium, nothing else. Okay. And the ratio between the magnitude of transmitted wave and instant wave can be expressed like this. Okay, what is the basic assumption we made to get this? First, we assume that the wave we are handling is a planar wave or plane wave. What is another assumption? The medium is governed by linear acoustic wave equation. That means we are assuming small amplitude, small acoustic wave, right? In other words, the magnitude of pressure is not more than, for example, 130 dB. Okay? And what other assumption we made? For example, when we have this kind of surface, that is filled by another medium, and this characteristic of the impedance of this medium is Z1, and the characteristic impedance of this medium is Z0. Okay? First, the general wavefront may look like this, no longer plane wave. But we can argue that this kind of wave can be decomposed into the superposition of this wave and this wave and this wave. Therefore, studying this type of planar plane wave upon this discontinuity have some value, and we can argue that way. Okay, then can we assume this kind of irregular shape discontinuity? Can you assume that as if straight line? Anybody had an idea? Can you assume it? What I'm saying is, this is too simple. This is too ideal, right? Ideal, but studying that kind of example is very good to understand some basic physics behind transmission, reflection, so on. But you can argue that, hey, this is too simple to understand what we normally have in practice. And the result that we learned from this kind of simplified, idealized example does not help us to understand what will happen when I have plane wave over here, for example. Okay. So this is general discontinuity. Okay. More specifically speaking, I want to say this is general impedance discontinuity or impedance mismatch in space. And we want to know what would happen when we have this kind of impedance mismatch in space. And I first argue that this kind of a general wavefront can be decomposed using Fourier series or transform into many, many plane waves. Therefore, assuming plane wave certainly possesses the physical meaning. And my next question is, how can we consider this kind of discontinuity? Okay. First, what we can assume is the wavelength we are considering is much larger than typical irregularity of discontinuity. Then we can assume this kind of discontinuity like this. Do you think that is possible? Certainly possible. For example, this kind of discontinuity is 1 millimeter. I mean, from here to there is 1 millimeter. And the wavelength we are considering is, for example, 100 hertz. Then the wavelength is what? 3 meters. Then, what did I say? 1 centimeter? Huh? Millimeter. The millimeter is nothing else when like 300 hertz whose wavelength is 1 meter. When 1 meter C, 1 millimeter, it's nothing else. So in that kind of situation, we can regard that kind of discontinuity as a flat surface of discontinuity. Okay?